Yeah, so welcome. My name is Benoit Alain. I work at Starpod Studio in Montreal, Canada. Have been for the last 6 years. And during that time, I was during most of that time, I was lead programmer on Castle Story, which is one of the games that we worked on the last years. And so in that game, you want to build castles, you control agents that build them for you. And actually, you don't necessarily tell them how to. You just lay out what you want to build, and they will decide where to find the resources, in what order they want to build it, and all kinds of stuff like that. That requires pathfinding. So really, pathfinding was one of the big challenges we had while developing the game. And about 2.5 years ago, we kind of made huge changes to the game, which included this new algorithm that we developed. And I'm hoping that this will interest you and maybe of use to other games that use voxels. I'm going to show you a video of our game to give you an idea. Okay, so here's a couple of screenshots from the game. You can see in terms of pathfinding, there's a staircase there's a suspended bridge, there's a couple of people running around, there's a bunch of furniture in the room on the right. Here we can see the player has placed a number of blocks. The characters are trying to build them. We also have a door that locks 2 sections of the castle. And we have people working in the woods to chop new resources. We also have combat in the game. Players like to build giant castles. Did I mention it played on flying islands, and the landscape is important to us. So players tend to kind of put their castle in a strategic place. They farm the terrain. They build all kinds of stuff. So the game is really dynamic. And it's also a large-scale type of game. The players can dig outside. Well, they can kind of empty mountainsides and stuff like that if they wish to. And they build giant constructions in general, which span over a large territory. So if we think about pathfinding, what we've seen so far, we have many agents. They may want to avoid each other. They may travel in groups. We have dynamic obstacles in the game. That's objects that have a behavior that changes over time without necessarily the player interacting with them for it. So doors that can be locked, but also barrels that can be moved around, and all kinds of other objects whose behavior is unpredictable for characters. We also have castle mechanics. We have stairs. We have blocks on which you can climb. And we also have voxel mechanics. So the terrain is deformable, and we have buildable blocks and that kind of stuff. Also, since we're developing a game, we're concerned about performance, as always. So the game happens all at once on a large scale. Like there's things happening all over the island. There's a lot happening at the same time in the game. The player can kind of teleport at each location to see what's happening there, and the characters have to be, able to be credible at every location. And so when the pathfinding is updated for some reason, it cannot interrupt the game. The game has to continue its pace. And also the characters have to naturally react to the changes in whatever the paths have changed. So let's talk about pathfinding. My presentation is going to be broken down in this way. So start by talking about the problem, then our data structure, then how we do pathfinding with it, then some examples from the game, a bit of analysis on performance, and some conclusions. So this is a bricktron from the game called Norma. Brictrons can move around. They can pick up bricks. They can move behind walls. They have friends that they might want to not bump into. And when characters think about how they move in the game, they use what's called a path. So they use a sequence of voxels that they wish to walk onto. And as you can imagine, paths can be elaborate and hard to calculate. And that's a general problem in computer science and game development, which is called pathfinding. So we can think of a path as in terms of a two-dimensional diagram like this one. Essentially, what we find in these diagrams, we'll be able to apply it in the 3D world afterwards. So this is a typical A-star algorithm behavior. So we have a source and a destination. It's one of the popular pathfinding algorithms. It tries to go in a direct way towards the goal as much as possible, but if there's an obstacle in the way, it will expand its already explored path in all directions equally until it finds the actual shortest path. And as you can see, if the obstacle is large, it can become a bit inefficient. So this is what is called an A-star trap. It's pretty frequent, and if it's heading for the goal, but it falls into a dead end while doing so, then it will explore the entire dead end. And in this case, it's going to be long. So it happens in Castle Story all the time. This large island chunk here was explored for no apparent reason, except that they had to conclude that it wasn't the right path. So it's really inefficient. And also, it's kind of by design that it happens in Castle Story, because like the players want to wall themselves inside their castle. So characters will bump into that kind of problem all the time. In the game, characters want to build blocks, so they need to find their resources. So in this case, even though the resource stockpile is close in absolute distance to the character, it doesn't mean that the path is going to be short. And characters have to kind of decide, like they want to find a path, and they have to like check as far as they need to find that path. So sometimes they're lucky and they'll find one. Sometimes they're less lucky and there is none. And then they will explore the entire map before they can conclude that there's no path, which is not really good. So it happens in a case like this one. This is one of our large islands. It has almost 1 million walkable voxels in it. So if there is no path between 2 points and you want to be sure of that, you have to explore the entire island. With A-star, it can take minutes to do so. So really the problem with A-star is the number of cells to explore. If there were less cells, maybe it wouldn't be so bad to explore in the dead end and stuff like that. So maybe we could combine cells together. Maybe we could have fewer of them. Maybe we can combine them hierarchically, more and more, until we have a very simple world. If we do that, we might be able to explore a dead end with only a few iterations, and it's not going to be such a problem. However, with the portrait I just pictured for you, like if you add detail, you're going to break your regularity. And even though I didn't change anything qualitatively, I kind of made it so that I could not explore with regular regions anymore. So we're back to square one. Well, in Castle Story, if we take a 3D island which has kind of a smooth terrain in it, well, it looks like this with regular regions. It happens that the voxels cannot be merged when they are close to a ledge, when they are close to a mountainside. You know, there's all kinds of bumps and 3D detail in the map, which makes so that even though at a glance the island will look very smooth, in fact, doing that regular region thing is just isn't so good. And if here we wouldn't find a path between 2 points, we would explore all the yellow cubes that didn't get merged, and in the end, we would still work for minutes until we could conclude that there's no path. So really, regular regions aren't so good for us. And the problem we identified is, especially when there's no path, what can we do? Like, can we have a kind of an easy test to at least say for sure, like, if there's one or if there's none? Maybe we could save something with that. So we're going to ask ourselves that question. Can we solve path existence first? And hopefully I can convince you that yes, this is the idea of how to do that with a simple hierarchy. So the idea is, instead of having regular regions, we're going to merge cells together. We're going to merge voxels into larger and larger regions by increasing local connectivity. What I mean by that is 2 regions are going to get merged if they have the same parent cell and they can be connected together without leaving that parent cell. So here at the level 2 picture there, we have regions 6 and 7. They share the same parent cell, They are connected if you kind of make a little way around the corner there, but they're not connected without leaving the cell, so they won't be merged. However, on the next level, they will be merged because now they share the same parent cell and there is a path within that cell. So in the end, at the top level of the hierarchy, we have exactly as many regions as there are disconnected islands or disconnected regions in absolute. So that's pretty nice because now we can say in a matter of a few iterations if two voxels are connected or not. We just go up the hierarchy. If they share a parent, then they're connected. Otherwise, they're not. And also a good thing about that hierarchy is it's easy to update if you change the terrain. If we add a wall here, we only have to regroup those voxels that touch the wall, that have, not that touch the wall, but that share a cell with the wall that was added. So here you see that the number of regions that are touched by this process at each level of the hierarchy is going to be roughly the same. It's not going to grow exponentially. And the same goes if we remove a wall. Here we see that the change that was local at the first level is still going to remain a local change at each of the levels. So in the end, we have an exponential effect, but we only have a linear cost. Or I should say linear in terms of layers of hierarchy. Okay, so I think we have a way to determine path existence in this simplified version of the problem. But it would be nice if that way could also bring us an actual path, not just tell us if there's one. So yes, we can have a path with that method. And I'm going to show you how. This is just one way to do it, and we're going to talk all about how to do it efficiently and in a better way in a few slides. But for now, the way to at least guarantee that we can find a path is the common parent method, I call it, which is just you start by a point, you go up the hierarchy, find a common parent, and then you go down the hierarchy to the destination. And this gives you a hierarchical path. So what we do with that hierarchical path, we refine it. So we start by removing the top layer and finding a subpath within the layer underneath it. And then, again, we find other subpaths on the layer underneath the previous layer. And those subpaths always remain within the parent cell that was on the previous layer. So we don't have to explore everywhere to build those subpaths. And then at last, we have a walkable path. So I'm not saying this is the best path. I'm just saying this is a valid path, and we have it for free, or mostly free. So can we do something with that? Can we implement that in a real game with all kinds of characters running around and, like this is just a theoretical model. We want it in 3D. We want it to work. So yeah, let's do it. All right, I'm going to break this section into 3 parts. So building the hierarchy, updating it, and using it to pathfind. So this is a typical scene from Castle Story. We have a dynamic obstacle that is a door here. We have a couple of agents, workers. We have a few blocks on which you can climb. We have blocks on which you cannot climb because it's too high. We have walkable voxels and non-walkable voxels. So how are we going to build our hierarchy? The first step is to identify all the walkable voxels and create a pathfinding node for each of those voxels. These are going to be the nodes at the bottom of our hierarchy. So all of the walkable voxels are the voxels either from the terrain or from the blocks the player have created that have no other block on top of them. So all those that have an exposed upper face, essentially. Now we have those nodes. We want to connect them together at the lower level of the hierarchy. So we build neighbor connections. And generally, it's a pretty simple and straightforward process. But just keep in mind that there are special permissions required for some connections. For example, climbing up on a block or jumping down one of them, or whatever other gameplay design wants to implement with pathfinding. So we have to bear that in mind and encode that in our neighbor connections, and it will come back later in the talk. So once we have all the nodes, we need to put them in the context of a larger grid, larger voxel grid, because we want them to be merged eventually and do other layers of the hierarchy. So we have the X, Y, and Z position of the node, and we can kind of infer from that by just dividing it by 2 and like rounding down. We can infer in which cell it's going to lie, and each subsequent level of the hierarchy is going to work the same way. So once we have identified all the voxels in a single cell, we can try to merge them together. So this is an example where we have All those voxels, we're trying to merge them in as few groups as possible, but we have a number of rules that we need to respect for that. So we want to have local interconnectivity. What I mean by that is the three voxels at the bottom can be reached from one another without leaving the cell. The one at the top, though, it can be reached, but we would have to kind of go up the slope on the side, and that would leave the voxel grid, the cell. The other way to reach it would be to climb up that dirt block there. Some units may be able to do it, but not all of them in all situations in the game. So we want to be conservative here. We want to only make as many groups as there are qualitatively distinct situations in terms of pathfinding within our voxels. And so for each of those groups, we create a parent node. In general, there will be more parent node than grid cells that are not empty. Here I have included some implementation tips. I'm not going to go through them like during the talk because they're kind of more in-depth details. I want if people are watching this on GDC Vault, they can pause the video and maybe read them. But essentially, they're not essential to understanding. So once we have our parent nodes, we want to build our neighbor connections for the parents. And so we're not going to explore the neighbors like geographically this time. What we're going to do is use a simple trick. We have the connections from our children nodes. Some of them were leaving their parent cell. And so those that are leaving their cell will become the parent connections. So I illustrated them in yellow arrows. So all those yellow arrows are the nodes, the connections that leave the cell. They will become the connections for the parent nodes. Oh yeah, a quick note here. So I said earlier that there were going to be special permissions for some types of connections. Well, we have to respect those. So if there are many different types of connections that leave the one cell and goes in the other cell at the child level, all those connections need to be respected and maintained at the other level afterwards. So the parent connections will encode multiple permissions combinations. Okay. So now we can just generalize this and go up our hierarchy until we have as many levels as needed by doing the same process. Okay, so maybe we need to update our hierarchy. Maybe some things have changed. We have built a beautiful bridge in the middle of nowhere, and a catastrophe happens, the bridge explodes, leaving a giant crater and a few loose blocks. What do we do? Well, we start by identifying all the voxels that were affected by that change. So all those that changed, that were walkable and are not anymore, or the other way around, or maybe they have new neighbor connections. And now, well, one way of doing it would be just like to remove all those nodes, the old nodes that were affected, and create new nodes at the same location, which we are going to have to reinitialize. Later on, I'm going to talk about the fact that we can not do that and use pooling instead, but just briefly. But essentially, we destroy the old nodes and we create new ones. And so those are the voxels that changed. And here, you may have noticed there's a few blocks lying around. Those are loose blocks, and they are generally dynamic obstacles because they're affected by physics, so they're kind of unpredictable. And so all the structures that the player builds and all the loose blocks are, for now, they're not part of the hierarchy. They're dynamic obstacles which are going to intervene during the pathfinding process later. So just keep in mind that our hierarchy is just for terrain and blocks. It's going to actively ignore those other details for now. Okay, so now we have to rebuild our connections. So all the new nodes need connections from the old nodes, and the old nodes need to know the new nodes. And those new nodes have to be situated in their larger voxel grid, form new groups, which is going to give birth to new parent nodes. And those parent nodes need new neighbor connections as well. And then we can propagate that through our hierarchy until we have all our layers. Okay. So hopefully we have built a hierarchy of nodes of increasing size, and we can use that to navigate and to do some pathfinding. So that's going to be the subject of the next part. Okay, so this is a kind of a debug of a path with a hierarchical path. So there's larger cubes that represent larger nodes. And it's not so important, just to know that in the game we have tools to kind of visualize this, and we're going to use them later in the presentation. So you remember the common parent method? We said it was a way to build a path. It's true. You find the common parent, you go up and then down to your destination, and you can refine it, and you obtain at the end a walkable path. But while doing so, we never left the region, we never left the area of the common parent. So what's to say that, like, do we know what was outside that area? Maybe this was the situation. And maybe the path that we found isn't the best one. Actually, it could be far from the best one. It could be really a bad path. So this method doesn't really get optimal paths for us. And we need a way to guarantee, or at least kind of control, the optimality of our path. So we need some rules. First rule, stop early. So suppose we want to explore a path to our immediate neighbor. Well, we could go up and then down, or we could just explore a neighbor connection that fits the distance to what we're looking for. And by doing this, we're not going to go all the way up the hierarchy and find a crazy, strange path that goes around and comes back. And we're just going to kind of go into incremental steps that correspond to the likely distance to the goal. And so the rule in general is don't go as low as needed in the hierarchy as you come closer to the goal, and more in particular, don't explore nodes whose diameter or whose, I guess, width is larger than the distance to the goal. And if there's multiple goals, then you can use the minimal distance. Second rule, be pessimistic. We don't want false positives. So these are dynamic obstacles from the game. We know that in the hierarchy they were ignored. So now we're not going to explore those higher level nodes that overlap on dynamic obstacles and that could give false predictions, false positive predictions. So the rule in general is go as low as needed in the hierarchy to avoid exploring nodes that overlap on dynamic objects. As long as these dynamic objects are blockers for you, so some dynamic objects could be all right for you to walk through. So we have kind of a method that we call for each dynamic object when we do the search to verify if that object is a blocker for us. And if it's not, then we can proceed. But if it is, then we have to go around it. So this is what it would look like in our hierarchy. Instead of exploring the parent node that overlaps the door, we just go underneath it in the hierarchy, and hopefully we can find a way among its children to go through. And then we go back up until we reach our goal. So third rule, converge quickly. What I mean by that is, why go to the pain of building merged regions if we're not going to use them? So the moment we explore a larger region, we shouldn't explore its children regions, because that's the goal of the algorithm, basically, is to eliminate the children nodes. So in general, don't explore children nodes if you have already explored any of its parents' nodes. So the pink nodes here would be eliminated by exploring the green nodes. And oh yeah, one last thing. Now that we aren't using the common parent method anymore, we're going to explore a larger territory. So we're going to need a way to explore space, not in all directions at the same time without any kind of priority. We would like to have a pathfinding method that had some priorities and that kind of would converge quickly towards the goal. And we know a method to do that. It's called A star. So we're going to try to use A star with our hierarchy. We're going to try to have our own version of A star, which really isn't a different version, actually, but you'll see. OK, so this is pseudocode for A star. You've probably all seen it at some point. So we have a priority queue. We start by inserting a source. Then until the queue is empty, we remove the most prioritized, the top priority node from the queue. If that's the goal, then we're done. If not, then we extract all its neighbors, all the ones that weren't explored already, insert them back in the queue, and proceed until we find a path or not. In our case, we're going to need more than the neighbors. We're going to also insert the links towards the parent, the neighbors, and the children of the current node, if applicable. So the A star function, A star search works with a priority queue that has a penalty function that needs to extract the node with the lowest priority first. So generally, the penalty function works like this. We have a constant times the path, the length of the path, plus a constant times the distance to the goal, plus some, custom gameplay influence that design needs or wants to influence a certain path instead of another. So the first constant is kind of makes paths be as short as possible. The second one aims to go towards the target as fast as possible. And those notions of path length and distance to goal are key to make A star work. And so in the world of voxels, it's pretty simple. You know, distance to goal is just your favorite distance, maybe Euclidean. The path length is the sum of the weights of all the node connections from the source to the destination. But now we need that to work in our hierarchy. So to do that, we will introduce a concept called representative children. So a representative child is, so essentially all parent nodes have a bunch of children. They can have one of those children be their representative child. And if you follow the representative child of your representative child, and you follow that chain all the way down, you will eventually find a representative voxel. That representative voxel is useful because it can help you estimate distances between higher level nodes. So if you want to have better estimates, then you should choose your representative child to be the one that leads to a voxel as close as possible to the center. But that's not like absolutely necessary. It's just for better results. And once we have that, we have a way to ponderate the weights of the connections all throughout our network, and we can now use them for A star. So we have in this example, the level 2 nodes would be connected by connection weights that corresponds to a path within the level underneath it. So we have 2 connections here, and we can follow those connections to build a path with an estimated length of 10. It's not going to be the actual length, and we'll see in a second, but it's an estimation of the length that comes from adding all those connection weights of the representatives together. Also, we can use it to build a distance notion, which is just the distance between the goal and the representative voxel of the node that you are currently exploring. Okay, so I said it's an estimated length because in this example, for example, there's a shorter path that could just be a bit faster. But it's just those lengths are going to be used to drive A star, and since they're approximative, it kind of breaks the contract of A star that it will lead to an optimal path. It's not going to lead to an optimal path anymore. It's going to lead to a path that is approximately optimal depending on how approximative the weights were. So before I talk about how to quantify the optimality of your path, I'm just going to remind you that we still, through that A star process, we still obtain at the end a hierarchical path. So it's going to contain smaller nodes and larger nodes, and we still have to refine that path, like I said with the common parent method, to get a walkable path at the end. And that refinement process is not different from the one at the beginning. It does not involve representative children. If we were to connect the representative children, it would get a very wobbly path, and that wouldn't really make sense. So here we're just trying to find the shortest path that connects through the children to the next parent, to the next node of the previous level. So once we do that refinement at the end, we get a walkable path, and all of the lengths of the nodes of the connections in that path are going to be exact lengths. They're going to be exact weights, and they're going to build up to an exact path length. So we can estimate the optimality, or at least the approximativity, I don't know, of the approximativeness of the path that we obtained by doing the difference between the length estimation that we had in our hierarchy and the actual length that we obtained after refining. And this is going to give us an approximation of like how our path has good chances of being optimal, but it's not an exact science because like some things could happen where, I don't know, you kind of made a detour, but it so happened that that detour was the shortest path in the detour. And, you know, it's not an exact science, but it's a general good way to determine how likely your path is going to be bad. And if it's an important path, like the player has selected a character and told that character, like, go there manually, and it's a short distance, like even your approximate path is short, you know that if there's a better path, it's also going to be short, so it's not going to be very expensive to calculate. So sometimes in the game, we just say, okay, go ahead and do another pathfinding in this situation. We know it's not going to cost too much, and it may be a bit better. So just lower the hierarchy constraint and do another pathfinding. And if that's not enough, it's probably because you have some kind of design weight in your neighbor connections at the voxel level, which are very extreme. Like, absolutely never use that connection unless there's nothing else. well then, like our hierarchy tends to blur these things out. So if there's such a connection type, then there's ways to tell our hierarchy, we don't do that if possible, but we can force it to explore the lower level nodes anytime it tries to employ that connection type. But there's a trade-off between forcing those weight calibrations that maybe design once and like the cost of actually doing your pathfinding in the end, because you're going to ruin the hierarchical effect. So let me talk about a notion that is path unrolling. So characters can walk while they are refining their path. They don't need to know their entire path at first. And this is an example of a path that updates in real time. It's a hierarchical path, and it's on a pretty large island, but it's really inexpensive to calculate those hierarchical paths. And a character is hypothetically trying to use that path, but it's not using the refined version of the path. It's still using the hierarchical version, only it's refining the path as it is traveling. So you see here the large cubes are getting transformed into small cubes progressively towards the end. So this is what we would like to have. So if we're using that technique, we need to know that we need a bit of look ahead for the animations, so a couple of nodes in advance. And also, we can't use the path error unless we have some refinement going on. So the more refined the path is, we can kind of refine the top layers first and then some of the closer nodes. And so the more refined, the more precise the error calculation is going to be. And in the best case, a path of length n would be translated into a path of length log n. And we can spread the cost of those n nodes during the execution time of the path. So let me talk about path validation now. Like I said, finding a path is pretty fast, but executing the path, walking the path, can be quite long. So during that time, it's possible that the path becomes invalid. The terrain has changed or someone moved in the way. So here we have two groups of characters walking, and they're kind of blocking each other while they're doing it. So they're trying to validate and redo new paths all the way. It's a bit messy. You see that people are bumping into each other all the time. They're stopping all over the place. In the end, they do reach their destination, but it doesn't really feel right. There's something missing. So we don't like that so much. We have a technique, which is not very sophisticated, but it works. It's called path mending. So the idea is just you keep your path. You don't discard it. Instead, you try to mend it. So you try to find a subpath that goes around the obstacle. And if it still remains within a distance limit, it's going to be able to replace the other path reasonably. And while we're doing that, we have a nice strategy, which is to use a special A-star weight. That is the difference between all the weight that you added with your subpath and the weight that you saved along the original path. That makes so that if we reconnect further down the original path, we don't get penalized for it. So it allows us to get more natural looking paths with diagonals and all of those. So characters don't just keep very thinly close to the walls. And we can even add some penalties in places where other characters are about to move. And if we reach our limit and we find nothing, then stop moving and try default to the previous behavior, essentially. So this is what it gives with path mending. So it's a bit better, right? Okay, so we're happy with that, and we're going to move on. Okay, a few more tips. So agents, it's a bit like dynamic obstacles. If you want to avoid them, you need to not explore the higher level nodes in the graph. Enemy agents, however, can be treated like they don't exist, because when you meet them in the field, you're just going to defeat them and then walk over their dead body. So. Also, you can use pooling for the nodes, like I said earlier. You don't have to destroy and create new nodes all the time, but if you do so, be careful. You're not going to bump into destroyed nodes when you're executing your path. Instead, you're going to bump into outdated nodes, which is just that they have a timestamp that is younger than the timestamp of your path. And also now is the time to just remind you that when we were doing the A-star algorithm, we were exploring all our available neighbors. I said available because, yeah, you have to impose the branch permissions at that point. So you don't explore those branches that you don't have permission to explore. And if you remember, our connections had permissions that we spread through our hierarchy, so we can also explore parent nodes by imposing those permissions. Okay, a few more tips. So you don't need to use a priority queue if you know you'll explore the entire world. Let's say you want to collect all the possible items of a certain type and explore the world for that. You can also ignore the dynamic obstacles, like by default, if you know in advance that you have a type of search that only cares about terrain, for example. You don't need to store your paths all the way in the pathfinding process. You can kind of just, if you're just testing connectivity, you can throw the path away while you're building it. You can also fail early. You can conserve your path inside a volume or limit the length. Another nice trick, which is like not proper to my method, is to just, if you're looking for a path between A and B and you're not finding one, well, along the way you can take note of all the closest node that you explored towards B, and just at the end you have a fallback path that brings you from A to C, or from A to A prime. That is as close as possible to B, and it will feel in the game like this is an actual, like a good behavior for the character to go there. You can impose more precision. You can play with the A* penalty function a bit. So here we have in the game we don't have neighbor connections in diagonals. Instead, what we do is we just have a special bonus for A* when the node direction alternates. So it's a small bonus so that it doesn't break the optimality of the path, but all else being equal, the pathfinding will prefer to alternate directions instead of having long perpendicular lines. Because our animation in diagonal is a bit faster. Okay, and we can kind of play with other weights like fear markers that you can put so that when an ally dies, your character will try to not walk on those nodes. Okay, a few more examples. We tried having pathfinding for characters that are afraid of other characters and want to run away. In this case, it's a bit different than just having them like being magnetically repulsed, because if the character ends up being cornered, they will just find a way that confronts the enemy and goes behind them. The way to do it is just you use the enemy as the target, as the destination for A*, and you use a negative weight for the distance to the goal. So then it will path away from the enemy. We also use pathfinding to map construction goals. So in the game, we need to know like what resource is available for what block. We can just start a global pathfinding request with all starting points, well, with all resources and all blocks being starting points for the search. And the search is going to expand from all those points at the same time, and they will meet in the field at certain locations. So we create connectivity sets for all those places where they meet, and at the end we have a global portrait of all the resources that are connected together, and we can redo that, I guess, on a regular basis in the game to get an update of what's connected. It's pretty cheap because we have a hierarchy to do it, so covering our entire map is really not that expensive. Another thing we do is we have enemies spotting the weakness in your wall by having them be able to navigate, in their head at least, through your wall. And we just have like crazy high connection weights inside the walls, inside the bricks for the enemies. And so they think they're going to be able to pass through the wall, and they are going to move inside your castle by moving in the breach, which is the weakest. And when they do arrive at the wall, they will start hitting the wall instead of walking. It's part of their walking animation to break the wall. So it works. So let's talk about performance a little bit, and then we can end with that. Let's say we have one of our largest maps, which has about 1 million walkable voxels. Then A* will use 1 million nodes. We will use 1.5 million, give or take. In fact, this is an overestimation because each hierarchy level is going to be exponentially less. Well, it's going to be, I guess it's a geometric series, so each level of the hierarchy is by a constant factor smaller than the one before. Also, the nodes are a bit take a bit more memory each now because they need to have a connection to their children and a connection to their parent. So all in all, it takes about twice as much memory. As far as building the hierarchy, we build it from scratch at the start of the game. And essentially, the base nodes of the hierarchy and their neighbor connections are just translated from the map data, like the same data that we're using to build the geometry. We're using it to build the nodes. And then the group formation process I was describing earlier, it explores each node exactly once. So in the end, the total time that is required to build the entire thing is going to be proportional to the number of walkable voxels. And so there was a bunch of optimizations we could have done, like multi-threading, stuff like that. We didn't end up doing it because it was not our bottleneck. It just took like 20% of our loading time. And there was like, this is at the end after we have optimized other things. So, okay, as far as terrain modification goes, if you were to just modify one voxel, then rebuilding the entire hierarchy for that voxel in our game takes less than 1/10 of a millisecond. But that's proportional to the number of hierarchy levels. So like, it doesn't really help to have 20 hierarchy levels because there's diminishing returns. 6 to 8 is good enough. The thing is, if you modify several voxels, which are relatively close together, then you can batch those changes, and with some luck, all their parent nodes, when you're building back your hierarchy, are going to be shared. They're going to be the same nodes. So you don't have to build them again and again. And in the end, typically each voxel is going to affect only one level or maybe 2 levels. And so we can save 80 to 90% of the update time by doing that. And so when we profile our game, like the update of the terrain, the pathfinding part of the update doesn't really register in terms of performance, like geometry and colliders, physics, and all of that takes much more. So if we were to compare performance in terms of the search, let's say the worst case for an A* in a million voxel, in a million walkable voxel island would be 1 million nodes to explore. In our case, it's between 1,000 and 3,000. The discrepancy comes from the number of dynamic obstacles in your map. So when you start the game, maybe it's going to be 1,000, but as you play along, eventually it's going to go up to, for example, 3,000 because those dynamic obstacles prevent you from exploring your hierarchy. In the best case, A* is going to make a path of length n in n steps and iterations. In our case, if we use path unrolling, we will be able to build that path in log of n steps, which is, I mean, not a lot in either case. But the worst time for A* in this situation with 1 million nodes to explore would be 2 to 3 minutes because we don't want to interrupt the game. We assume we have only a limit number of ticks per frame, which is reasonable for characters to walk around and not make the game be slow. So here we say 100 ticks per frame at 60 frames per second. It's going to take 2 or 3 minutes for A*. It's going to take half a second for us. So yay. Okay, so what's good? The concepts are simple. We use no pre-computation, so it's useful for procedural world generation, for example. It's fast to initialize, it's fast to maintain, it's relatively lightweight. It is easy to extend, there's just a few classes. And most of all, it beats A* by a factor of 100 to 1,000 on average. So it really saved the day for us. There are some drawbacks, however. It's hard to guarantee path optimality, especially if we have extreme weights, or if we absolutely want to guarantee like very subtle weight, like to respect the weights very subtly. It's also a system that is voxel-based fundamentally, so it works for voxel games, and it feels a bit hackish to do our diagonals. And we couldn't really think of how we could do other curves instead, apart from having a post-process applied. It still is a performance bottleneck if we do our profiling in the game, because now that the system is more optimized, we use it a lot more, so it kind of came back in the profiling. We don't have larger units in the game. We only have units that occupy 1 voxel. If we were to have larger units, we would probably require multiple hierarchies for different unit sizes or special branch permissions for those units. Also, units don't dig as part of their pathfinding. because that would imply putting nodes inside the terrain. It would require a lot of memory. And also, there's no flying units in the game, and if there were, we would probably not use that method because it would be too many nodes in the sky. These are things that work with our method also, but we haven't had time to try them. Multi-threading, as I said earlier, infinite worlds where we could kind of load and unload sectors. I know it would work, but I mean, there was no need for it in Castle Story. Portals, that is, there could be neighbor connections at the voxel level that don't lead to a voxel that is adjacent. It would not break our system, but there was no such thing in Castle Story. And public transportation, I don't think I have time for that, so I'm just going to skip it. So thank you for listening. I would like to thank my colleague Fabian Di Tullio for spending a weekend with me brainstorming, reviewing my code, giving me some ideas, really off the clock, before I could present this idea to the rest of the team and make it part of the official project. I would also like to thank my colleague Germain Couet, who helped a lot with reviewing the visuals of the presentation and making most of the graphics. And this is my email, so if you are ever in Montreal, you can just send me an email and come visit our studios. Thank you. If you have questions. Just go to the mic, I'll be happy to answer.
You mentioned that physics was a larger performance bottleneck when it came to updating the terrain. Did you consider taking this similar hierarchical concept and applying it to your colliders? I know you didn't mention how your physics works. Yeah. But a similar model could be applied to other systems.
So let me rephrase that. So the question was, would it be possible to have a kind of a similar hierarchy or a similar system of simplifying things hierarchically with physics so that we don't incur so much costs by updating it? Like I said, it was one of our bottlenecks. The short answer is we don't have control over the physics because we're using the native physics engine that comes with Unity. We're working with Unity. There's a lot of things that we take out of the box from Unity, and there's a lot of things that we redo ourselves because it's our expertise, it's our field of expertise. So I think with a game engine, it's pretty much always like that. Like you kind of take whatever is not your expertise with you, and whatever you build better, then you can overcome what the engine gives you. So in terms of physics, we didn't really specialize the physics that Unity already offers. So maybe one day, but for now, no, we have no consideration of that, sorry. Good suggestion, though. Any more questions?
I'm not very clear about the node structure. Is it storing the pointers to the adjacent nodes? It requires 100 bytes per node. Is it?
Yeah. 100 bytes per node is an average because there are the base level nodes. So most of the nodes in the hierarchy are going to be level 0 nodes. And those nodes don't have any children. They just have the same neighbor connections as the A* node would have. So what's the cheapest way to store a connection? I guess there's a lot of different ways that you can kind of know that you have a smaller sector of the world, so all those nodes are going to be indexed with a smaller number of bytes because they are within this sector. So there's all kinds of ways that you can minimize the use of memory to build your node to be as cheap as possible.
If it is just storing the connectivity about the adjacent nodes, so I think you may, I don't know if it's possible to just store the bit mass about whether it it connect to the right, connect to the left, so you just have a few bits to...
Yes, at the base level, yes. So, but not at the higher levels because, I mean, there is no limit to the number of neighbors that you can have at the higher level because the nodes are not going to be, you can think in your head as though they are increasing, cubes of increasing size, but it's not actually the case. There are irregular regions of local interconnectivity. So there can be multiple irregular regions that suddenly at a certain level become all interconnected. It's possible for a node to have like 12 children and like 20 neighbor connections. Just by pure chance, like just by the patterns that they form while they are not grouping together. So you can't predict the number that there will be, but in general it's going to be 4 or less in general. So maybe if you have a special kind of type, like you said, like you encode your neighbor connection on 8 bits, or 4 bits, like in the hope that it's going to be the general case, and if it's not the general case, then you have a subclass that handles that. That could be possible. We didn't go very far in optimizing the memory because it's, like I said, it doesn't use so much memory, and eventually the pathfinding system is going to be bound by the tests that we do on the dynamic obstacles as well as the hierarchy itself. So, I mean, in the end, it's a big mixture of a lot of game elements that influence how our characters behave.
Okay,
and like saving a bit on this is not really worth the effort. Well, it didn't turn out to be our bottleneck when we optimized the game.
Okay, thank you.
More questions? Well, I think we're done with the time anyway, so thank you.